Welcome. In this lecture, I want to introduce something called binary operations. These are not foreign. It looks like a very strange definition, but this is something that you've seen many times. Addition, multiplication, function composition sometimes when you're talking about the right set. Okay, so here we go. So suppose that S is speaking of sets, suppose that S is a set, so suppose S is a set. Okay, then by definition, we're going to have that a binary operation on S, so I'll make our binary operation green, so a binary operation on S. Oops, that was supposed to be red. Just gonna slit. On S is a function, so is a function F going from, oops, I didn't leave enough room there. Okay, so it's going to be going from S cross S to S. Now, it seems like a simple definition, but there's actually a lot to unpack in this definition. So here are a few things to kind of focus in on. So I said it has to be a function, right? So it needs to be well defined. So needs to satisfy all the well-defined properties a function satisfies. So properties, all the well-defined properties a function satisfies. Right? In particular, one of them is that your output, right? So your outputs must always be in S. And so this is what we would call closure, okay? Right, or you would say like an operation is closed, okay, when your outputs are the same, okay, and our inputs, right, are also, so our inputs, so inputs are a pair of elements of S, right? And order matters, right? Because this is a Cartesian product. Okay. So we're inputting two elements of S, and we're getting out an element of S. And if it's, kind of in a situation where one should be checking this, you should check that it actually satisfies all the properties of being well defined. Okay, so let's, all right, so i.e., what are we going to have? We're going to have that, let's do this in green. As long as we're talking about the binary operation. Okay, so it outputs an element of S right, for each pair. Okay, and outputs an element of S for each pair order matters of elements of S. Okay, so let's think of, our favorite that we didn't even know yet, so our favorite examples. Right, could be, so one would be our set S is going to equal maybe the integers, right? And our binary operation equals addition. Okay. We could also do our, maybe we don't even need to just restrict to the integers. So maybe our set S is equal to the real numbers. And our binary operation is multiplication. Right? What can't we do? So what would be a non-example? Right? Because our outputs have to stay there, so it would be maybe for our set S to equal the integers, and our not a binary operation, so let's do it not in green. So maybe we'll do it in blue. Our not a binary operation, so not a binary operation is division, right? And we'd say the integers are not closed under division, right? And the reason is the outputs aren't integers. So outputs aren't always integers. So the outputs aren't always integers, i.e., we would say it's not closed under division, i.e., z, the integers, is not closed under division. Okay. So binary operations are a very special kind of function. They're going to satisfy a lot of properties, and we're going to use that. You've seen them before. So you've seen them with addition and multiplication. You have to be careful. You do actually have to be closed under your binary operation. And so that's going to show up a lot. And not every operation you could think of where you input two things and output one thing is a binary operation, because they have to satisfy this thing called closure, meaning that your output is the same S as you inputted to it. Okay, so I hope that made some sense, and I will see you in the next lecture. Sure.